Now let's talk about linear programming. Linear programming is very close to linear algebra. And it has this primary component called the objective function. It's just a function, but the point here is to either maximize the function or minimize the function, given some constraints. So for example, let's say you want to transport, or let's use the shipping, right? Like in e-commerce. And there are some constraints that have to do with petrol consumption, the distance traveled, the weight of the ships, the distance to the recipients. So you have these different constraints, and you want to select the parameters such that you're within what we call the feasible region. I'll show you an actual example of this. I'll show you both the mathematics and the graphical explanation, because graphing is actually a big part of linear programming, especially graphing inequalities. Like I said, linear algebra is a subset of abstract algebra, and abstract algebra is a development, or takes the ideas from classical algebra further. Also part of classical algebra is functions and graphing them. When it comes to vectors in particular, one technique that we will look at, which has applications in computer vision and natural language processing. By the way, one of the things that we'll be working towards is neural networks. So this is it's also machine learning. Part of this course is understanding machine learning, but neural networks specifically, not supervised and unsupervised learning. We'll be working with vectors. So we want to apply techniques like cosine similarity, which I said has applications both in image recognition and NLP. But a prerequisite for understanding vector operations is trigonometry. And trigonometry in turn has geometry as a prerequisite. What I'm trying to say is this. If you've ever enrolled in a course or picked up a book on linear algebra, it is assumed that you know all four of these, at least to the extent that would allow you to read that book or complete that course successfully. What I have done in this course is I have made supplementary material for all four of these. So for example, if we come across a word like a vector space, the word space comes from abstract algebra. And if you do not know what that is, because you have to know what that is if you want to make progress, well, then you can refer to the supplementary material, which talks about words like spaces and the axioms that apply to such a type of set. A space is a type of set. And of course, in order to understand the axioms that apply to those sets, you need to know some classical algebra, but nothing difficult. It's very straightforward. In fact, we can cover the key concepts here today. And then there's trigonometry. Trigonometry is a big deal. Again, because vectors, must be, what are the applications of vectors, whether it's computer vision or even PC, by the way, uses vectors. If we want to know how close they are to each other. So we need to understand angles, the sine and cosine functions, and for that we need to understand some basic geometry, or at least the notation in geometry. This again will be provided as supplementary material. So this is an example of linear programming. Let me give you a pictorial representation, and then I will take you to Markdown, because through this exercise, we will get a sense of what systems of linear equations are, which is from linear algebra, and the objective function, which is linear programming. So, we learn two things with one example. We have some function that we need to optimize. To optimize means to at least pictorially graph it so that it satisfies all of our four constraints. So we have these four constraints. And this function, particular function that we talked about, has two variables. Okay, so put differently, it's a function of two variables. Two variables will affect its maximization or minimization. Let's pick a hypothetical example. The price of a smartphone. It could be a function of the size of the screen and how much memory it has, random access memory. Or what's another example? Salary. It could be a function of how many years of experience you have and how many years you've spent in school. So academic experience and work experience. Okay, so that's salary would be we would say that salary is a function, and it's a function of two things. Anyway, here we have a function that is whose variables are x and y. Both x and y must be 0. So if you see here, if we graph the inequality for x0, x greater than 0, then everything in the right quadrant, in the first quadrant and the lower quadrant would be highlighted. Okay, so anything that is x, anything that is equal to, or that's an inequality. I hope the picture is not very clear, but that's an inequality, and it includes 0. It's not a strict inequality. So anything from 0 or above x will be shaded. Then we have y. Y must be above 0, right? So y is this vertical axis. Anything from 0 or above will be highlighted. But now we have two constraints. If we take these two constraints together, then if we just focus on these two, then how do we satisfy both of these constraints? Well, the shaded area must be above the origin for y and to the right of x. So in other words, we will have this region. We're basically slicing the shaded area. But then there's more. Here we have this other inequality. 2x plus 5y less than or equal to 3,500, which gives us this inequality. It gives us this graph. So not only does our solution must be in the right quadrant, in the first quadrant, we also have this, vertical, this diagonal line cutting through it. So if we have this quadrant, we must also slice it from here. And then there's this fourth quadrant. Long story short, we must perform arithmetic operations on these constraints, which are inequalities, until we find the roots. And once we find the roots of these equations, we will then have found the feasible region of our objective function.